for being a bit late, but we should be at around 100, so it's quite nice. Quite bigger, but it takes some time to get you all in. So welcome to Madeira. This is the second summer school for ISIS, which is also for the first time in Portugal, which is happy for us. And we are here at Colégio dos Jesuitas. I will just quite fast on this because we are really late. But this building belongs to the University of Madeira. It has more than 400 years, if I'm not mistaken. So it's quite an important building here for the island. And going fast through the program, So today we'll have the 3 lectures. First by Professor Constantino Sutis, then we will have Pedro Camanho, Professor Pedro Camanho, and finally Claudio Ruggieri. In between these, don't forget that we will have a very nice coffee break and lunch that I hope that you enjoy. And in particular, at the end of the day, we'll have a very nice dinner close by, just by the sea. It's 10 to 5 minutes walking from here. The restaurant is Vivaldi. At 8 p.m. should be okay. And we have chosen this particular day because there will be a firework show. They call it Atlantic Festival, that I hope that everybody will enjoy. It's a kind of competition between different countries. I don't know which country is today, but I'm sure today is Portugal, so it's even better. I hope that everybody will enjoy. And tomorrow we'll return at 9. Then we'll have Professor Alexander Sedmike and Mordecai Pearl. And you have remaining information in your bags. If you have any questions, please let us know. And thank you for being here.
I can speak from here. Well, good morning to everyone. So, PhD students, participants on this summer school. So, I welcome you, all of you. I hope you enjoy very much this 7th summer school. You enjoy Madeira Island. So, we have 5 lectures, as Professor Pedro already said. So, we are going to start with Professor Sutis. Well, they are well-known professors and researchers, so I hope you enjoy and it will be fruitful for all of you. I think you should put questions, you should put your doubts regarding your works. So I'm sure you are going to engage these 5 lectures, these 2 days of this summer school. So with no more delays, we are going to start with Professor Sutis. Professor Sutis is a well-known professor in the area of material composites. So he's director of and co-founder of Manchester Robotics Limited and professor emeritus of aerospace engineering at the University of Manchester. His research focuses on damage mechanisms of lightweight materials and real-time structural health monitoring. He has authored or co-authored more than 400 listed papers, which is a huge amount of research and investigation, and successfully supervised over 40 PhD students. So the Academy's fellows represents the nation's best engineers, research, innovators, entrepreneurs, business and industrial leaders. So Professor Sutis is one of them. And well, no more delays, so I will invite Professor Sutis for the stage is yours. You can start.
Thank you so much. Thank you. Great pleasure to be here, guys. I was really surprised actually that you have received your certificate before attending my class and before sitting the exam.
Nobody will be, don't worry.
And before sitting the exam. So I would like to ask you now to bring them back, hand them back, our certificates. No, it's too late. That's no good. Let me find my presentation here now. Okay, excellent. Oh, that's and that's the end of my talk. So how many compositologists do we have? 1, 2, 3, 4. This is it. That's about it. So my talk is about composites. Design of carbon fiber composites. How we can make them tougher? Because the perception is that they are relatively brittle. Carbon fiber. So today the lecture is how we can make them tougher. And we walk through different options that we're having. Come from the University of Manchester. And Manchester is famous for no, it's more than that. Which going to tell me a few things that Manchester is famous for?
Football.
Football. Oh, okay, football. How many teams do we have in Manchester? 2? Wrong. Bring your certificate back, please. How many teams do we have? How many football teams do we have in Manchester? Only one, Manchester City. Manchester City. All right, this is outside Manchester United, but it's only one team, Manchester City. But away from the football, it's Britain's first university in the industrial age. And it's the place, of course, where we split the atom. What else? The first computer, Alan Turing. I mean, again, the perception is that splitting the atom took place at Cambridge. That's not true. Hasn't Google. Anyway, materials at the University of Manchester is strong, from lightweight alloys and composites for planes, trains, ships, and so on, to high-temperature materials for jet engines and power generation, electronics, ceramics, and polymers, biomedical materials, textiles. Manchester is famous for its textiles and composites. So for those that are not familiar with composites, what are they? Composites combine the properties of 2 or more materials with different constituents. Any two materials, metals, ceramics, polymers, elastomers, glasses, will be brought together and you design the composite. They might be mixed in many geometries, particles, chopped fibers, woven architectures, which again you need to use your maths to optimize the fiber architecture in order to design the material system, because composites are not materials, they are material systems. You design them to create a system with a property profile not offered by any monolithic material. In mechanical design, it's often to improve the stiffness to weight ratio, or strength to weight ratio, or improve toughness. So we have designers here. Do we have some kind of civil engineers or mechanical engineers? And when you design something, you design for strength, for stiffness, or toughness. Sometimes you make compromises and you need to do this, you need to do that, and you do that. In thermomechanical designs, you reduce thermal expansion or to maximize heat transfer or to minimize thermal distortion. And composites, of course, do that. What are the benefits? The biggest one is you reduce the weight. They provide, especially carbon fiber, high strength and high stiffness. You can tailor their properties. So the design you design, you're tailoring. When I go to Max Spencer to buy my trousers, I am 34, 33. I go there and pick it up and put it on, it's fine. But the rugby player, he is 34, 33, but has big thighs. So going to M&S to buy a pair of trousers is not good. It's not going to fit. So where's he going to buy his trousers? He needs to go to the tailor. Yeah? So that's the whole idea of when we build the composites, we are tailoring. Yeah, you become tailors. Using composite, you can reduce part count or metallic equivalent. You can reduce machining. They do not corrode in aggressive environments. And they provide very good fatigue resistance. At the level, they offer you the potential to embed functionality. So you can build your multi-layered composite and you can insert sensing elements. You do real-time structural monitoring, for instance. Where they use extensively in aerospace and defense, energy, wind energy, marine, construction, transportation. We have some civil engineers here. Do they use any carbon fiber composite in that construction? No. We have any people from Switzerland where they build bridges actually using carbon fiber ropes. And while people know and they have heard of composites, when you look at commercial products, very recent, the first commercial product came out in 1983 when Dunlop produced the first carbon fiber tennis racket. And a decade later we have McLaren, the Formula One car, where they used carbon fiber. But now we have reached a stage where people are looking at the alternative fibers. And here's an example where the Porsche 709 GT4, that's not the one that they want. Academics cannot afford that. It's all natural fibers. And more specifically, they are flax fibers. And those fibers that work fine, where there is less need for weight saving. Yeah? Because it's heavy. But there's not better for one application, you're fine. But if you try to use flax fibers from Formula One, it's not going to work. It's going to be relatively heavy. So carbon fiber composite is strong, lightweight, relatively cheap to manufacture. Relatively cheap to manufacture compared to forming metal. Because now fabrication methods have made so much progress that the cost has been reduced dramatically. So it's cheaper to manufacture with carbon fiber polymer composite rather than metal. And it's basically unbeatable when it comes to making a race car model. If you want to win the gold medal in the Olympics for cycling, you're not going to use steel or aluminum alloy or magnesium alloy. Your first choice for material selection is carbon fiber. Of course, if you have an accident like President Biden, President Biden, then obviously the hit damage then is quite difficult to repair, to fix. So composites enable innovation. Here we can see the winglet of the Airbus A350. How big is that section? How long is that section, the winglet? What's the purpose of the winglet in the aircraft? Why do we put that? Do we have any aeronautical engineers?
Create the turbulence flow.
To reduce vortices, eliminate vortices, to reduce drag, to improve fuel efficiency. So it's about 7+ meters. It's a big structure. Have you traveled to the Airbus A350? No? I used to break in my lab big beams for the wing design. So this is the complex inlet duct manufactured by ADP. ADP stands for Advanced Tape Placement. This is the inlet duct of the F-35. As you can see, it's very complex shape. If you're trying to build this from metallic alloys, you're going to lose the stealthiness of the aircraft. It's going to be too heavy to take off. And here is comparison between a metallic and non-metallic aircraft. The Boeing 787, the new Boeing 787, it's not showing you anymore. It offers you a big view, a big window. And the smaller one is the window you get when you travel with the Airbus A380, where the airframe is mainly metallic. And why did I put this picture on display? What is the message I'm trying to pass to you? What I'm trying to say? Well, you see this comparison. The designer.
That we have more possibilities for designing components.
Yes, but what's the main purpose of that? What does it tell you? I have a big piece of material, and I cut a big hole. I remove material. What happens to its strength? It gets weaker, does it? Because you create a bigger hole. But here the designer of the 787 introduced a bigger hole and removed more material because he is confident that the performance of the airframe is not going to be affected. He is trying to tell you that carbon fiber composites do not fatigue. They do fatigue, but not as much as metals. Yeah? And the next picture it shows you fatigue. I mean, if you look at the most basic laminate configuration of the 090 laminator, you're going to see you apply uniaxial tension, static loading. The first type of damage you're going to get is in the form of resin cracking. Your polymer is weak, yeah, it's going to crack, and that's what you get. And at the tip of the crack, you develop a three-dimensional stress field. And those stresses need to be calculated. Because if you don't calculate them, you don't know what's going to happen next. And what's going to happen next is that at the tip of the crack, you have a three-dimensional stress field. Can you see my pointer there? No, of course not. Oh, what's the point of driving to screen so you don't see my pointer? But they have to be there. I want to move around. You have to come up with a better solution, mate. That doesn't solve my problem.
There are new presenters. There are
New presenters.
No, new presenters who basically, you see there is also this electronic presenter.
Exactly, and then communicate, the two screens communicate. So when you have time, exactly, so can you see my pointer there now? Still I can't see. So at the tip of the microclass, all those stresses, maybe they're not high enough to break my steel fibers, yeah? But they are high enough to debond, to separate my neighboring plaques. And that's what I call, that's going to be, it's my local delamination, yeah? Delamination, separation of the neighboring plaques. And that is going to reduce my stiffness. What is stiffness? I mean, people, civil engineers keep talking about stiffness. What kind of property is stiffness? Which going to define stiffness? What is stiffness? Right, come on, here, someone got the responsibility. Tell me what is stiffness. Resistance to deformation, it says. But is stiffness a property though? What kind of property is it? It's a material property. No, it's not. What is it? Huh? Plus geometry is material plus geometry. Yeah? Is material plus geometry. The last modulus is material property. But once you say stiffness, someone is going to say, is it a flexural stiffness? Is it membrane stiffness? Is it torsional stiffness? What kind of stiffness is it? Yeah? Because I can employ a low modulus material, but I can bring in geometry and make it flat, whatever. Yeah? And that's going to increase my flexural stiffness. We're going to bend it, and it's going to bend because it's got too much weight. Yeah? It's too hard, right? That's going to be too heavy, and I can't do that in my aircraft construction. Yeah? Because we develop and design for minimum weight. So I'm looking at specific properties. So it's going to affect all the elastic properties, the Young's modulus, the axial direction, the transverse direction, the shear direction, and so on and so forth. Plus, of course, that kind of damage is going to allow the environment to get into my constant structure. So it can be quite damaging. And then structures, they're not just under uniaxial tension, they are under biaxial loading or multi-axial in-plane and out-of-plane loading that introduces additional stresses. So if I apply tension now in transverse direction, the zero layer is going to split. I'm going to get axial splits, and at the tip of the split there, I'm going to get more delaminations. And this type of raised microcracking can also occur due to thermal loading. You can bring your laminate out of the autoclave, out of the cooking oven, and those thermal stresses can be high enough to break the polymer. Usually we use epoxy resins. They usually crack at about 5,000 microstrains. What's 5,000 microstrains in specific spray? 5,000 microstrains is 0.5%. Yeah, so it's relatively low. And then, of course, the task we have is how to design cathode resin systems that they will crack, but at much higher, at light strain. So, just under tension, damage mechanism, maybe cracking, or degradation of the overall stiffness properties, in-plane, flexural and torsional of the laminate, introduce development of other damage modes in the lamination, which then eventually is going to lead to fiber breakage and catastrophic failures. Are you doing stress analysis? Can you do using abacus, ANSYS? Yeah? I mean, all these are closed form solutions. It's all done by hand. Yeah? Do you recognize any of those equations? What's the top one? What is it? What's the top equation of that? What does it represent? When you solve a structural problem, how do you start? What are the steps that you follow? What's the first thing that you write down? You write down equilibrium of applied loads, external forces, and internal stresses, or equilibrium of internal stresses. That's equilibrium of stresses. All right? And here, I have an element which is cracked. I have the matrix crack that we've seen earlier, and the local delamination that starts from the tip of that crack. And the purpose of the exercise is to start writing down my equilibrium equations, my compatibility equations. What are the compatibility equations? What do they relate? No, compatibility equations, they relate strain to displacement, because applied loads introduce deflections, displacements in my structure. So I apply load P, P or F force, and I get displacement delta. The material now feels some kind of pain, and that pain is expressed in terms of stress and strain. Yeah? I hear your mother sometimes says, it's too stressful for me, there's too much stress in me, going to break down. Yeah? Okay. Don't give me so much load. Don't put so much pressure on me. Do they say that? Okay. It's the same with structure. So if I step on this, the structure feels the pain. That pain is expressed in terms of stresses, and the structure will start feeling strain, and that strain, when it exceeds certain material value, like the resin, exceeds the strain, ultimate strain can sustain and get a crack. So you write down equilibrium equations, materiality equations, carry out the problem, solve the problem. What do you do next? You write down the constitutive equations that relate what? Exactly, they relate now stress to strain. And the most famous law, the most basic, fundamental constitutive equation is Hooke's law, which it says what? Stress is proportional to strain. And that, so sigma is equal to E modulus times epsilon. But that is for a very specific case. Which case is that? Is a 1D stress analysis, assuming that the material is linear, elastic, homogeneous, isotropic. Yeah? And the composite is none of that. But the steps, of course, are exactly the same. Plus, of course, I have to solve the problem because I have to solve the stresses in the presence of the matrix cracking and the delamination. Yeah? So, eventually, once I solve that system of equations, what are the unknowns I'm trying to solve in the structural problem? Stresses. And once I know the stresses, I can go back and calculate my strains. And once I know the strains, I can compare that to values I have for that specific material, and I can determine if it's going to break or not. So here, this bottom equation, yeah, gives you all the stresses, J2, J takes values of 1 and 2, so it gives me the shear stresses and the transverse direct stresses that are responsible mainly for opening that crack and creating the delamination cracks. And I think send some papers for you to read, and they have been uploaded on the system, and you can have access. So once I got the stresses, then I can calculate my strains. Once I know the strains, I can calculate the reduction, the effect of the striking, the delamination on the density modulus, the one direction, the transverse direction, the shear modulus, the Poisson ratio, and so on and so forth. So I have my entire stiffness matrix of my anisotropic composite. Yeah. So this is the stiffness matrix of the Davis lamina, in this case, of the theta lamina. In this case, theta in 6 hours is 90 degrees. And it shows you what happens to the axial modulus as I increase the crack density, cracks per centimeter. And the same if I have delamination, that Q matrix is going to be affected by the presence of the matrix cracking and local delamination. And of course, most of the published papers out there, like say the top one, Tsai and Daniel, people still use. Most of the models, they focus just on the elastic modulus, E. While we know very well it's also the shear modulus and the transverse modulus and the Poisson ratio. When someone does an FE analysis and tries to account for damage and reduction of those elastic properties due to damage, they assume that I lose 10% of my axial modulus, 80% of my transverse modulus, 20% of my shear modulus, and another 10% of my Poisson ratio. And the problem is, in a cleft configuration, the Poisson ratio might go up. Might go up by 20% or 30% in the presence of damage. Yeah? Damage might, yes, reduce your transverse modulus and the axial modulus and the shear modulus, but not necessarily the Poisson ratio. The Poisson ratio might increase that configuration. What are the limits of Poisson ratio in the astronomy? What kind of values do you get? No? What are the values of Poisson ratio? The limits, the lower limit and the upper limit? Minus 1 to 0.5. And you can prove that. Otherwise, you can leave back. But I can design my composite with Poisson ratio of 13. It's up to me. I'm the tailor. If I want a big Poisson ratio, I can design it. Have you heard of authentic materials? Have you heard of the authentic materials? Authentic materials, they have a negative Poisson ratio in the form of when you stretch it, instead of getting thinner, it gets fatter. And when you compress it, it doesn't get fat, it gets thin. Because it does have a negative Poisson ratio. And we can design materials with negative Poisson ratio, because that's what I need in order to achieve certain acoustic properties. So here, this guy, Tsai and Daniel, in 1991, they developed this top equation for the reduced shear modulus in the presence of matrix cracking in the zero phi and matrix cracking in the transverse phi. So they've done first for just matrix cracking in the 90-degree layers, and they had the first term. And then they added an additional term of similar expression for the effect of splitting or matrix cracking in the other phi. But those guys, Castellan and Suits in 2000, they said, no, because once you have the crack in the 90s, it might affect also the way the other ply splits. And it's not just by adding an additional term, you have this term due to matrix cracking in one ply, and then you add another similar term for the matrix cracking that takes place in the neighboring ply. Because there is an interaction effect, and this is the interaction effect. And now, of course, if you don't have longitudinal cracking, then yes, both models they reduce to the same equation. But the top model is wrong. It underestimates the shear modulus, or overestimates. It depends very much on those terms. Depends on the layout. And of course, now you have the effect of relative lamination area in an already cracked laminate where you have 3 cracks per centimeter density, crack density, and you can see the normalized stiffness property by how much is reduced, yeah, the axial modulus and the shear modulus. But the Poisson ratio is not reduced, it goes up. But you need to understand the physical meaning of the Poisson ratio. What's the physical meaning of the Poisson ratio? What is Poisson ratio? Don't just tell me, tell this to the class. So those guys over there can hear you. Come on, stand up and talk.
Finalization tells how material will expand or contract, then apply a certain amount of a strain or stress.
Did you follow that? Can you be animated?
No, not really.
You don't be animated. Who can be animated and let me explain to me the physical meaning of the Poisson ratio? You can do it with your neighbor and try to stretch your shirt or your blouse, yeah, and see what happens when you stretch it in one direction. What happens if you cover it in the opposite direction, in the transverse direction? What does it do? So if I apply, say, 1% strain in this direction, and my material is not osmotic, yeah, 1%, and the Poisson ratio is traditionally, say, for an isotropic metallic material, what is the value? Yeah, what's the value that we use for the Poisson ratio of steel? 0.3. Everybody knows that. 0.3. Yeah. What's the modulus of steel? 210 megapascals. Yeah. What is the Young's modulus of a 0.90 plus minus 30 laminate? Symmetric lam. You don't know because it's not any more material, it's a system. Yeah, and you calculate it. Anyway, going back to our Poisson ratio, so I apply 1%, it contracts by 0.3%. So the transverse strain that the material experiences, yeah, is 0.3%. Because the Poisson ratio tells you by how much you contract or expand in the opposite direction of your apply stress in this direction. So with the time configuration, in an anisotropic plate, like say, it is isotropic 0 to 32 minus 32 symmetric. So how many layers I have in that laminate? I have 2, 4, 6, 12. Thank you. And I have cracks in the plus 30 and minus 30. I have 3 cracks per centimeter. And I have an amount of local delamination we've seen earlier. So obviously, you apply 1% strain in this direction, yeah? And the modulus actually, the Poisson ratio, changes, increases instead of reducing. Because you don't know how this construction is going to move. You need to calculate it. You need to run those equations. And then, of course, once you have performed your stress analysis, you can do your fracture mechanics now. You can calculate how much energy you require to grow 3 cracks per centimeter with 20% local delamination. Because already you know the applied strains, already you know the reduced stiffness matrix of your laminate, the Q matrix now, yeah? And you can estimate how much energy you require to reduce that amount of damage. And then of course, if you have a critical value for that energy parameter, you can tell if the laminate is going to fracture catastrophically due to that damage or not. Or not fail, but propagate. So you use the energy-based failure criteria, which is, in this case, is a very basic one. It says when this strain energy release rate associated with local delamination exceeds this GC value, critical value GC, which is, it's not a material, but it's a laminate property, yeah? Then that local delamination will propagate. or the whole ply will delaminate. And of course, people, they develop, of course, everybody likes to develop closed form solutions and try to simplify things. And in this case, we have my friend Kevin O'Brien. He's a NASA guy. He's done lots of work on delamination and modeling delamination and all that. And he expressed this GLB is the strain energy release rate associated with local delamination. Yeah? And it tells us for this kind of carbon epoxy system, AS4 3506, 3506 is the polymer, is the resin, is the epoxy resin, and the carbon fibers. And this is the layout, 0 to 25 to minus 25 to. I mean, nobody in industry, in Airbus or Boeing, they use this kind of layouts. What are the layouts that are currently used? 0, 90 plus minus 45. And why they do that? Why they use 0, 90 plus minus 45? Because they try to build something that resembles isotropic material properties and aluminum. So they compensate. But then it's not sad because when you try the airplane, you have but sometimes you play safe, but it doesn't mean you're safe, yeah? Things can go wrong, so it's better to educate people to do this kind of analysis. Anyway, so that model, as you can see, in the Nash configuration, he uses only the effect of damage on the elastic modulus in the direction of the load. But we've seen already that the laminate, although you apply only uniaxial tension, you introduce the matrix cracking and the local delamination, and it affects the axial modulus, the transverse modulus, the shear modulus, and the Poisson ratio. Especially when you have plasmanesthetic applies. And then in this case, his model is telling us that the energy required to introduce that much of delamination is 12 to 21 megajoules per square meter. Yeah? Which is a lot of energy. But if you do the proper way, where the entire of this matrix is affected by the damage, then it's not 12, but it's 0.32 or 34 or 36 megajoules per square meter. So the material, the laminate, provides actually much less resistance to that formation of local delamination, to that interlaminar. We have two types of cracks, we said. We have the intralaminar. What's the intralaminar cracking? Intralaminar cracking, when cracks grow within the ply, and interlaminar cracking, when cracks grow between the plies, which we call it delamination. Yeah? So the model, the simplified model, dramatically overestimates the energy absorption of that laminate. And then, of course, we go to another type of loading, compression. And Jack? Where is Jack? Who goes Jack? When we try to characterize aluminium, do we focus on compressive properties, compressive behavior? Have you seen any papers on the compressive behavior of aluminium, or steel, or any other metal? No. Why is that? They're not interested? They don't care?
Compression strength is much higher.
It's much higher because if you have, say, a manufacturing defect, you have a macro crack in your aluminium alloy or magnesium alloy or whatever, other compression, what's going to happen to the crack?
Close.
It's going to go close. It's not going to propagate. So the designer assumes that the compressive strength it's going not to be higher, it's going to be as high as the tensile strength. And that's not the case in composites. Reinforced with continuous fibers. Because the compressive strength is 30 to 40% lower than the equivalent tensile strength. And the reason is, although you have performed your oil and bucking analysis, and you have made sure that my structure, my strut, my beam is not going to buckle, macroscopically, it's not going to satisfy oil and bucking. Did you hear that I was asking you earlier? Did you do any compressive tests of steel or aluminum alloys? No, it's not silly to do compressive tests.
There is a low Shinga. Low Shinga effect.
Yes.
This is a test in compression. It is important to assess the reduction in compression yield when you first apply a tensile yielding.
Okay, but we'll just tell you about the actual compressive properties.
Is the idea that you can diminish the compression yielding factor if you apply first the tensile
Yes, but that's for different metals. Where you're looking at the properties, material properties, chemical properties.
That's for the stiffness.
Those different, but also the strength.
And I don't believe it doesn't change the relative strength, but it gives.
But you try to say you stress it in order to improve the use.
The contrary, we will reduce the compressive yield but first the tensile.
Yeah, but that's different. Different story. Obviously, when you're trying to measure the compressive strength of steel or okay. So here now, you have designed your beam, the composite beam, to go to a market. So it's not going to work by oil market. Yeah, because oil market is geometric property. If you're doing this too long, and petrol will reduce, eventually you get much and you break. But here, still, the continuous fibers can fail at the fiber level in the fiber level. So, if you have a crack, a neighboring defect that reduces the lateral support of the resin that provides you a fiber, then it will fail with fiber micro-buckling. So this is a buckling mode, damage mode. This is a fiber instability damage mode that reduces its strength by 30 to 40%, because the amount of the system and the kind of the resin you have, the type of fiber, the fiber, and so on and so forth. And again, you need to develop, you need to perform stress analysis. And what are the 3 steps of our stress analysis? The set of equilibrium equations, probability equations, procedure equations, and then what do? You apply your kinematic boundary conditions. You tell the analysis or abacus how the structure is supported. Yeah? Otherwise, you cannot solve a number of certain equations for the set of unknowns you have. Yeah? And this is what we do here. Do you recognize that equilibrium equation, that final equation is a 4th order differential equation that when you solve, you calculate, what do you calculate? You calculate the stress in the zero ply that supports the axial load, isn't it? The zero layers that parallel to the loading axis, that they take all the stress. So you need to calculate this stress, sigma zero ply, and when it exceeds that 1600 megapascals value or 1800 megapascals value, depends very much of the strength in compression of that zero layer, then fiber micro-buckling will take place and the whole laminate will break.
So, Professor, what do you mean by macro-buckling?
Micro-buckling is a fiber instability mode. The fibers, here we have already, even before you started your test, have you seen any carbon fiber pre-preg that comes out from the manufacturer? And have you tried to put it into the light and see if the fibers are straight or not. And actually they're not, they're kind of wavy. But when you make a laminate and it goes into tension, this fiber waviness, initial fiber waviness you have, straightens up because the fibers are stretched. But in compression, if you have, say, 2 degrees of fiber waviness, and then you apply a compressive load, already the fibers will bend further and further, and will fail in the form of coil and vacuum fiber. And this is the SCM, is the king band, where at the point where you have the vacuum deflections, the fiber breaks and creates this king band, which is actually, in the microscope, at a lower magnification, resembles a fatigue crack in metals. And it propagates the particularly applied load. And when it reaches critical length, it goes boom. And the decibels that it creates, that kind of fracture, it releases all that energy, that we try to calculate, and we need that as well, is equivalent to the decibels created by the takeoff of Concorde. How many decibels is that? How would it be with time? All time is not a parameter. So it's about 150 decibels, kind of thing. How many decibels the washing machine? It has speed. 85. You see? And stop criticizing us that we don't do the washing, right? We do, and we know actually the number of decibels. So the 85 decibels, probably you will get when you get the creation of moment elimination. About 60 decibels is generated when you get metal scratch. 60 to 80 decibels. Why is this relevant? Why is this relevant?
Detection.
Ah, very good. Because on this damage now, you can visualize it because you go either scanning the microscope, or you destroy the structure, you do spectrography. Those cracks are invisible, you don't see them. But we try to detect them. And we need to develop a real-time SHM methods to make sure that our structure, when the pilot does a maneuver outside the flight envelope that the designer tells him not to do that, but he's a pilot. The pilot goes outside the envelope sometimes, overstresses the structure and creates hacking. And as we have developed data, the non-destructive testing, but real time, we hear those cracks. To listen to those cracks. And when we get cracks with an energy of 150 decibels, we say, hey, we have broken fibers here. And we need to find them. How are we going to find them? So, solving this fourth order differential equation, I can divide the stress, critical stress, into 0 fibers, 0 ply, and I can determine if fiber vector vacuum is going to occur or not at that specific applied load. Which is going to make my day and tells me the principle I have used and applied to solve this problem. This is a classic paper. Goes back to the No. This equation is Timoshenko beam on an elastic foundation. Timoshenko took the equation to solve the problem for a beam on elastic springs. This is now using the same principles. Is the Timoshenko beam theory, but on a non-elastic foundation, because as you can see, the shear modulus G of the material varies with applied load, applied displacement. So V is the applied displacement introduced by that compressive load. And V naught is the initial fiber imperfection, fiber misalignment, fiber waviness, which again, you need to detect non-destructively. Good luck, mate. Yes, and that's why those engineers there, Buzz and Boyd, they stick to 0, 90 to -45. Yes, so this shear modulus of our beam, is the shear modulus of our epoxy resin, and it's non-linear because it's not the elastic value I use, but the shear modulus, if you look at the stress, strain, shear response, it continuously changes. Yeah, if you take the tangent, so that's what it does. It takes into account the variation of the shear modulus as a function of the applied load. And here, this step here, are the interlaminar shear stresses developed at the free edge of the laminate. Because if you do a steel plate, if you're a civil engineer, you do the stress analysis of this, you don't care about stresses at the edge. It's a stress-free edge. But not in the laminated configuration. You develop those interlaminar beasts, the tau ZX and the tau ZY, especially the tau ZY is going to introduce additional waviness into my already wavy fibers. And it's going to destabilize those zero fibers, which is going to affect the stress at which fiber manufacturing will take place. And then, of course, once you have the critical stress that the zero ply will buckle, you can calculate the compressive strength of any bidirectional laminate plus minus theta. And all this damage that we're talking about is a non-visible damage. Here is a 0 plus minus 45 free symmetric laminate 3 millimeters thick, which is loaded in compression and has been loaded at 90% of its ultimate compressive strength. And there is no damage, or at least non-visible damage. I mean, someone is going to say, yeah, I can see little damage there, but maybe that's due to the drilling process. And then when you try to visualize the damage using the computed tomography, X-ray computed tomography, then what do you see there? What do you see there? Who's going to tell me? Who's going to describe? What do you see? You see actual cracks in the zero ply, off-axis cracking, because of minus oxidation, because already we've said that the people develop properly develop over delamination. So those cracks are surrounded by delaminations. They cause local delamination, separation of the plies. Which of course, when you're in compression, it means that now your zero layer that supports the actual stress has lost its lateral support and will buckle earlier. It will micro-buckle earlier. So that local delamination reduces the support of the zero plies, frustrating the effect of the zero plies that they carry the actual stresses, and will reduce the strength of my multi-sectional laminate. And if someone has a very experienced eye, they're going to see that somewhere here, there is already fiber micro-buckling. That crack that goes transverse to the applied stress and propagates across. Yes, I had shown that already. I'm repeating now. There. Can you see? Can you see? There you go. That's the crack. That's the crack. What I did there? There, I have removed ply by ply. I have removed the off-axis layers. Yeah. Very carefully removed them to expose the zero plies. And this is the crack. And if you look at that low magnification of optical microscopy, you're going to see something that's loaded in tension, and you get a transverse crack at the edge of the hole propagating across. And when it reaches a critical length, ductile story. Have you done ductile? No? No ductile? In metals? So I use ductile there. I use some of the concepts of ductile. But under the SCM, that crack is not just a tension crack, it's a compression crack, and it's the fiber microvacuum we've seen earlier. The fiber instability head alone. And I used fracture mechanics concepts developed for metals. So can you see we learn from that community? But we have to adapt, we have to introduce the right changes to account for the new system we have created. So I replaced that damage zone with a linear damage zone that initiates at the notch, at the edge of the hole. And of course, I apply compressive loading, but the fibers that we try to buckle, that we try to break, they provide resistance, and that's the traction distribution that describes the load transfer characteristics of this local damage zone, which of course will dictate how successfully you predict or you estimate the compressive, overall compressive loading. Yes?
Where did you see this crack in the which lead is the seen clearly?
In the zero class.
Okay. And
Because you remember, the main stress component is axial compression. So it's the zero plies that sustain and support much of that applied stress.
then if we open the hole in the plate, we should change the direction with the flattened angles. 45 is flattened, right?
Yes? Because again, it provides better lateral support to your zero plat. Yeah? And we've seen that earlier from the prediction, didn't we? There. Of course, the lower angles of axis splice, they are better. 45 is here, and we use 45s because components, they're not just under axial loading, but they are under shear loading. And plus minus 45s, they provide higher shear resistance. So in the composite skin of your aircraft wing, the wing bends, yeah? So you have flexural loading that produces direct stresses, but also you have twisting, which introduces additional shear stresses, because the flexural loading introduces shear stresses as well, but not to the same extent when the wing twists. And the plus minus 45 plus, they provide more torsional resistance to that applied twisting moment. And here, of course, this is fracture mechanics course, isn't it? So I'm trying now to calculate how much energy is absorbed by the fiber microvacuum, or how much resistance the fiber microvacuum provides to the propagation of the damage. Okay? So the fiber bends, it breaks, the fragments rotate, they lock. If they lock, of course, they provide more resistance to the applied load. And then if you look at the local stress displacement curve, it looks like this. Alright? But we know very well that those fragments actually they do not lock because the surrounding place, in order to allow this rotation of the zero fibers, they have to be laminated. You see that in our X-ray CT. And since they laminate, it means that those fragments they follow. And they don't really do this local aspect. And it's used mathematically for me actually to assume a linear reduction in that resistance that the buckled fibers provide, and see what kind of values I get for the overhaul compression and how it compares when Jack breaks those laminates and measures the strength. Ooh, we're fast. So I do this. So that's the clock, and that's the energy. So that's the energy absorbed or dissipated, or the resistance, if you like. Depends very much on how you want to define it and to understand it better. And I do more calculations. So now here, I'm not talking about anymore about crack opening displacement, but I'm talking about crack closing displacement. Because I'm in compression, and that crack goes part of fibers, they close. And we provide resistance, and we measure that resistance. So I can calculate the critical crack closing displacement in terms of time for diffraction level of the fiber, the exponential of the fiber, yield stress of the resin that supports the fibers, in order to calculate the amount of energy dissipated by the fiber microbat. And that's about, in terms of fracture toughness, it's about 45 megapascal square root meters. Depends very much on the layer. And here, that's the most important one. If you look at metallic plates with an open hole, you have two criteria. One is the ideally notch sensitive, which is the bottom one. Sigma notched over sigma unnotched varies with stress concentration factor 1 over kT. So this is the notch sensitive. The bigger the hole, the bigger the stress concentration, the lower the strength. And this top one is the ideally notch insensitive, which means that sigma notched over sigma unnotched varies with 1 minus R over W. R is the hole radius, and W is the half width of the plate. Yeah? So you remove more material, linearly your strength is reduced by that amount. And now with the composite falls somewhere those two ideal cases. The ideally sensitive and the ideally not insensitive. And the task of the designer is how to set up layups that they approach the upper curve, which is the not insensitive curve. And of course, this is a critical parameter. The overall elastic modulus of your laminate in the loading direction, the GC, the critical strain energy release rate associated with hyperbarometric, the unknotched strength, and the geometry. So if I put lots of plus minus 45s, I can create a more notch insensitive case. So we spoke about the invisible damage that damages our laminate. We spoke about how much energy is dissipated in all those damage mechanisms, which are very important. And we spoke about how we can optimize our design in order to make our composite more notch insensitive. And what do we mean by notch insensitive? This is the notch insensitive. This is lots of notches, lots of holes, but the aeroplane can still perform its functionality. What's its functionality? What's its purpose? It's to go out and kill. That's a flying gun. This is the A-10. Do you recognize the plane? The American A-10. That's the way it came back from one of its missions in Afghanistan. That's what it looks like. And this is a motion sensitive structure. Yeah? It doesn't feel the pain. It doesn't feel pain. So damage, impact damage is a critical one because we said that relatively brittle materials. You drop something, it causes cracking, laminations, damage, visible damage, which of course in our labs we can repair them. We can recover the strength, the stiffness, the shape, but not necessarily the aeroelastic properties. And that's why Boeing or Airbus, they will advise you, sorry mate, you cannot touch up your vertical fin, your composite vertical fin. Yeah? I prefer you to buy a new one. Because at the end of the day, the manufacturers, they're not interested in repair. But of course, they have a good reason for not to allow anyone to touch up their composite Airbus A350. Because yes, you might have the shape, the strength, the stiffness, but what about the elastic properties? Because maybe now, the way you transfer load, the load goes now into a weaker area, because your repaired region now probably is stiffer locally. And the cracks are going to grow somewhere else where they find weakness. And you don't know where they're going to appear. You have no control. So they prefer you to buy a new component. And this is like the case, because this aeroplane was somewhere in Africa, the landing process, and explosion took place, because just a couple of triggers of explosive stick to the frame. But luckily, it didn't explode at 40,000 feet, because if this happens at 40,000 feet and you get this kind of hole, the whole aeroplane will disintegrate. But once you are depressurized, you come down to land, this is what you get. Yeah, don't ask for the passenger sitting next to that window seat. But at least the rest of the plane landed. And of course, Airbus introduced, in order to make tougher systems that they can sustain this kind of thrust, explosion, absorb this type of energy without getting perforation, we have a glare system, which is a glass fiber aluminum reinforced. So you get the tactile behavior of your aluminum, of your metal, and you get all the benefits of your composite, which is the lightweight structure, which dissipates energy in the form of matrix structure, splitting, delamination, fiber breakage, but without getting perforation. And here's a carbon fiber metal laminate we have tested in our lab, where we can see that the composite splits. The aluminum undergoes extensive plastic deformation, but overall you don't get perforation. And that's another way of increasing toughness and making your composite tougher. Because you remember, we said that composites, they are material systems, and you design them for a specific need that you are facing. And here another way of improving toughness is to go back to the design of the fiber matrix interface. Because you remember, those micro tracks start at that kind of level, at that kind of macro level. The fiber devolves from the resin. And here you can see an uncoated fiber in the left-hand side and a coated fiber that actually, in order to pull out that fiber from that block of resin, you require to dissipate more energy. It's much harder to get those micro cracks that we've seen earlier. It's not anymore at 0.3 or 0.4 or 0.5% strain, it's probably at 1% strain. And then another way is that when you get that crack, you have obstacles in front of the crack. And here we have small fibers, we have veins at the interfaces. So when the delamination initiates, it cannot propagate because it gets prevented, its propagation, from those microfibers that we have inserted at the critical interfaces, which are estimated from our stress analysis, and they tell us that this is the interface that is going to delaminate. And this is where the stress analysis becomes so important. And another way is, okay, delamination, separation of plies. What about if we have reinforcement through the thickness? So those plies then they do not separate, they don't delaminate. And this is where we have used advanced textiles. We use some of their machines to replace cotton fibers and new fibers with our man-made fibers and glass fibers, and create three-dimensional woven architectures that would give us the desired toughness. And here we compare a two-dimensional woven fiber laminate with a three-dimensional fiber architecture undergoing some kind of impact loading. And yes, both of them, they get fiber break, which is unavoidable because you have exceeded those critical values. But the 2D experiences extensive delamination in comparison to the 3D, which is reinforced with protein fibers. And then when we look at the stress strain displacement, we can see actually that this stress response of the plane with an open hole is very similar to the one without the hole. And this is what we talked earlier about the notch insensitive structure. You remove material and it doesn't feel the pain. So your laminator can support the load in the presence of a big hole. And this is because you have designed your three-dimensional fiber architecture where at the edge of the hole you don't have the stress concentration factor of 3, but you have the stress concentration factor of 1. You have no stress concentration.
Is it the same in compression?
You don't use working architectures in compression, simply because your fibers they are already distorted and wavy. Okay. And we've seen already what waviness can do. So now you have waviness within the fly, and you have the waviness with undulation, high undulation. But then it depends very much on how much compression resistance you need. Because you need to just say 300 megapascal and it's fine. But if you need, if you design compression strength base and you need 800 megapascal, you're not going to get it from the walls and architecture. 2D or 3D. But it works. And since we are Manchester is saying forward. We are paying Nobel Prize Physics year 2010. It gives me the impression that Manchester doesn't make much noise about our achievement, do they? Because today, what we knew about Manchester was not the split of the atom, not the first computer, not the 25 Nobel Prizes. It was going too fast. So graphene can improve composites. Personally, me, I don't use graphene to improve toughness, strength, stiffness, because already my carbon fibers give me that. And they can do that, but I think where graphene has an advantage is that I can introduce functionality to my composites. I can tailor now thermal properties, electrical properties, I can use sensors, graphene sensors, antennas, and so on and so forth. For those that they don't know graphene, it's two-dimensional material. It's an allotrope of carbon. Your carbon fiber actually has graphene on its surface. Are you familiar with any of these structures? Baggy balls, 0D, carbon nanotubes, 1D materials. So graphene is a 2D, graphite is a 3D because it's thick, it's fat. I mean, here we're talking about thickness, ply thickness of less than 10 layers, less than 30 nanometers. So that's why it's called this 2D. While the carbon nanotube is called 1D because it's long, it's got only one dimension, diameter, and of course, material scientists, some of the superlatives that they use is the thinnest, the strongest, the stiffest, the most stretchable, transparent. Yes?
I have a question to the slide before.
You've seen that?
No. What? No, can you go one slide back?
Oh.
Please? There is a
mistake.
No. What to the graphene slide.
Okay.
Here there is a 0, 1, and 3D.
Yeah.
And I am not so much into graphene or material.
No.
In material. But is there a particular reason why there is no 2D carbon, whatever?
Yes, there is 2D is the graphene.
3D is graphene
Yeah,
itself.
yeah, it's two-dimensional material, graphene. Graphene is defined as two-dimensional material, an atom of carbon, one atom thick. One atom thick! Whew! One atom thick. It's absolutely. So Young's modulus, can you measure Young's modulus of graphene? Yeah. Do you have that ability in your lab to measure the Young's modulus of graphene? If it's invisible, how are you going to see that flake? Yes, I mean, you need quite sophisticated atomic focus microscopes to measure it. So Young's modulus has been measured at 1 terapascal. Strength 150 gigapascals. What's the strength of aluminum alloy? Really low. But this is why I like it, because conductivity, I can make a polymer, electrically conductive, and I can increase conductivity by 12 orders of magnitude by having just 1% by volume of graphene in my polymer. And the application of that, next time that you drop your smartphone, did I drop it? But it's graphene reinforced, so it doesn't break. So can you imagine, you use a plastic screen, but how can you make it conductive? Because if you break, have you broken your iPhone? Anyone successfully broke? Yes? Okay, what did you see? Tell them. It's a glass, and under the glass what do you have? You have a thick plate of aluminum. You make it conductive and get the signals from the figures. Oh, there you go. It's not really broken, right? It's broken. Yeah, it's broken. Really? Oh, sorry. What happened? What's happened? It's not me. Was it me? Maybe I ran out of time. Oh, that's the problem. I have to stop moving around. What time is the coffee? Is it coffee time? Yeah. Can you imagine this nightmare for those guys that they try to capture me in video? So how can you make graphene? You can start with a block of graphite and start breaking small particles, So, okay, you can use it to chemical exfoliation. Those Nobel laureates, what they use, they were playing in time, you really have lots of information. You do more than work. So those guys were guys with their pencils and scotch tape, and they realized that, you have managed to exfoliate graphene from the block of graphite with that pencil. So next time you go to Stockholm, at the Museum of Nobel Laureates and all that, they have Manchester and they have a block of coal, that we use in barbecue, and they have a block of sellotape to demonstrate that you can use the I call it exfoliation, Scotch tape exfoliation technique. So you can exfoliate and you can have graphene. Or you can use chemical vapor deposition where you can put your material atom by atom. As a slow process, but of course now it's been accelerating and it has been scaled up. So people can produce lots of kilograms of graphene. So if you go to Google and say, send me a couple of kilograms of graphene, the next day, and after you have paid a couple of £1,000, you will get your graphene. But how do you know that it's graphene in graphite or graphene oxide or something else? Applications, lots of applications, sensors, special electronics, energy, batteries, composites, bio applications, like this one. Graphene filter, it's covered in tiny holes, just big enough to allow water through and small enough to keep the salt. Can you imagine? If you go to Saudi Arabia, the Saudis, they pay about 2 pence or 2 cents per liter for their petrol. Try to buy avian water. It will cost you a fortune. This is one of my aerial drones in my office. If I want to run it for an hour, I have to use tether and put it into the battery of my car and fly. Alternatively, you can use high-power graphene supercapacitors, and that would make batteries obsolete. Those Airbus A350s that we spoke earlier, carbon fiber wing, how do they protect themselves from lightning strikes? Last time I was trying to take off from Osaka airport, you could see the aircraft hit by lightning strike. That's a big problem. That's the Airbus A350 that we've seen earlier, not painted yet. So carbon fiber composite aircraft are currently covered with chicken mesh wire. Yeah. Copper mesh. Do you know those chicken mesh wire that they use? Yeah. That's similar. For protection against lightning strike, which means that they put additional weight on the aircraft. But not only that, this is the problem that Qataris have with their A350 at the moment. It feels off, the paint feels off. They complain to Airbus, and Airbus told them, sorry mate, your country is too hot. And the Qataris say, yeah, but you sold us the plane, and you said that it's going to work in our hot country. What about Norwegians, that they have very cold weather? Of course, these aeroplanes have been tested in cold and very hot environments. So this is the wire that the aircraft is covered, and then they paint it. And this is the paint peeling problems that they have. So you don't want to travel with an aircraft where you can see the paint is really long. It's not structural problematic, but we don't want to see it. So gaps in the metallic mesh is there to protect the carbon fiber plate from storms. Again, we go to the mismatch of properties, thermal properties. Paints weak addition to titanium rivets. Can you see the rivets? There is don't have any paint on the rivets. It's just completely peeled off. And all this could be contributing factors. So probably conducted graphene modified epoxy matrix provide protection. I mean, Fiat, they already use graphene modified paints for their plastic parts of their cars. Maybe Airbus would use that, and same for Boeing, who knows? There's the guy in the sport car. He visited the university recently. The lady in blue is our president. You see, we're very progressive in Manchester. Our president is a female. Graphene on the handle of the tennis racket. I asked the company why you do this. They said people buy it, you know, and pay for it. And for our graduates last year, you know, first time when they graduate, you know, after COVID and everything, their gowns are graphene reinforced, don't laugh. Graphene enhanced smart clothing. It's already in the market, guys. It's not lying. This is the first way of conductive fabrics that will carry heat or electricity around your body, but without any power source. No batteries. All right. So it transfers heat from the hot parts of your body, so you don't have to wear gloves. That's good. So for this one, for this graphene coated jacket, you pay £525. Challenges, many challenges, increased supply of raw materials, reduced material costs, reduced finished parts, processing cost, coated, we said earlier, peel off, paint. But the most important is designed to constant strengths, yeah, and not treat it as black aluminium. Machining, drilling, assembling, joining, repairs, NDT, SHM, whoo, many challenges. So if you're going to have a job for the next 100 years, move to composites. Graphene is derivatives, how do you know it was earlier is graphene? Like all carbons, manufacturer determines properties and cost, depends very much how much you prepare to pay. Comes design, I like this one, this one. 5 minutes. Okay. And as you can see, it explains, in order to characterize composite material, yeah, you need extensive testing. But this is where modeling becomes so important. How to reduce the amount of mechanical tests you perform. This is the testing pyramid. You do about 10,000 tests to characterize the properties of the lamina. Nobody does these days, tests for aluminum alloy. That's Airbus, orders the aluminum alloy. Manufacturers providing all the best fundamental properties, all the right top environments for the aluminum alloy. You cannot do that with composites because composite presents not a material. Composite is a system. You design it, you are tailoring properties. The manufacturer is going to tell you for which layout configuration, which fiber architecture, which box resin, which fiber system. But modeling can be used extensively to reduce the amount of testing, not to eliminate testing, because still we need to calibrate some of our models. So although confidence in failing criteria is relatively low, modeling can reduce testing. Okay? We have diverse staff, we have students, and student body strengthens our research and enhances our students' learning. We come from all over the globe. Thank you so much, guys. And sorry for taking up more time than
presentation, this talk. So I don't know if you have any kind of questions or comments. Anyone?
Yes, thank you for your presentation. And I just have a little question because you talked about composites with epoxy resins. So we know that today it's very important the recyclability of materials. So we know that now there are a lot of research about composites with thermoplastic resins. It is possible, for example, that use graphene for this kind of materials, or we don't know yet, or it's something that is being looked for.
Yes, some of the thermoplastics. We have used graphene for the electrical properties and for the thermal properties to introduce functionality to those systems. So yes, you're right. The graphene is not just for epoxy systems. I think the polymer I showed earlier, it was polycarbonate, which is a thermoplastic. So you can use graphene also to reinforce any kind of matrix, provided that you can dilute it, you can uniformly distill it. So thermoplastics typically they have much higher viscosity than the thermosets. So the task is how to avoid agglomerates, creating lumps of graphene, and how to create the uniform distribution of those graphene layers. And again, we have published a paper on this that shows the way, and also have a video clip later on when we have discussion or time that allows us to do that. We have used graphene to create networks that are connected so you can transmit electric current, which is goes to the application of the electrically conductive paint for your polymer composite component, aircraft, whatever. Yeah, very good question.
Well, I think we should finish here, so now it's time for the break. Please go outside and